Hello, everyone. Welcome back, and thank you for joining us. I'm Steve.
I'm Scott.
And together we are
Backyard
Musings. Science and technology. You got it. I always say this, interesting. They're all interesting to me. Plasmonic modulators are tiny devices that convert electrical signals into optical signals for transmission through optical fibers. Until now, no modulator of this kind had been able to operate beyond a terahertz, equivalent to over 1 trillion oscillations per second. So think of this as, think of this just like this. Remember we did that segment on that fusion rocket that they're going to be using in space, and we thought, okay, when it hooks up in one space station in orbit, then it'll take it to the next space station in orbit. So that's what this is like. This is what you need to get from the chip to the optical whatever, and then back to another chip. So I don't know if that just confused you more, but hopefully that helped.
It sure confused me, but that's okay.
However, researchers led by Jürg Leuthold, professor of Photonics and Communications at ETH Zurich, have achieved this breakthrough. Previously, similar modulators were limited to frequencies of 100 to 200 gigahertz, making this new development 5 to 10 times faster. And I just want to put it out there, we are not propagandists for Switzerland just because this dude was in Zurich, okay? We're not. Would you like to know more?
We would. These modulators serve as crucial links between electronic and optical communication, enabling the transfer of large volumes of data. Quote, data is always initially present in electrical form, and nowadays its transmission always involves optical fibers at some point, explains Professor Leuthold.
The next generation of mobile communications, 6G, will operate in the terahertz range. Its backbone, the cables between the base stations, relies on optical fiber technology. We all know that. Quote, our modulator allows radio signals and other electrical signals to be converted into optical signals directly and therefore efficiently, says Yannick Horst, who worked on, I'm not making that name up, Yannick Horst, who worked on the component during his doctoral thesis.
Although the transfer of terahertz signals onto optical fiber is already possible from a technical perspective, it is a laborious process and currently requires several expensive components. The new modulators can convert the signals directly, reducing energy consumption and increasing measurement accuracy. Moreover, different components are currently needed for different frequency ranges. The new modulator can be used with any frequency from 10 megahertz to 1.14 terahertz. Quote, we cover the entire frequency range with a single component. It's therefore extremely versatile in terms of applications, says Horst.
Okay. Other potential applications include optical fiber data transmission within and between high-performance computing centers, because we've got a lot of data centers. They're popping up everywhere. Last but not least, the components are also of interest for high-performance measurement technology, including imaging techniques in medicine, spectroscopy, methods for material analysis, baggage scanners at airports, and radar technology. Some devices of this kind already operate in the terahertz range today.
The new modulator is a teeny nanostructure made up of various materials, including gold, and makes use of the interaction between light and free electrons within the gold. The technology was developed at ETH Zurich, which I think we've talked about before, right? And the device
sounds familiar.
Yeah, and the device was manufactured by Polytron Technologies, an ETH spinoff that emerged from Leuthold's group. At present, the company is working to bring the terahertz modulator to market so that it can be widely used in future applications in data transmission and measurement technology.
Yeah, so this could be, I mean, it's stepping forward to give us faster communications. So I like it.
maybe we're going to know it before it even happens. That would be cool.
Yeah. So just on an aside, want to talk about when we were driving here in our electric truck, because it's really comfortable. We don't want to drive in the Volvo. That's for commuting. So we saw this new car called the Lucid, an electric vehicle made by Lucid Auto Group. And what caught my eye was when we were backing out, the rear tail light had this red light that kept going back and forth. And I said, honey, doesn't that look like a Cylon? And she said, yeah, that looks like a Cylon. And so we started Googling, and it's using new technology batteries, which we've reported on before, solid state. And its top model can get 514 miles for its charge in its battery. So it's got a lot of batteries, or high density batteries.
Wow.
And it can charge 200 kilowatts in 10 minutes. 210 minutes. So 20 minutes, do a full charge, 20 minutes, you're gone for 500 miles. Or
Wow.
450, whatever.
What's the range on your Lightning F-150?
Good question. To give you some perspective, I've got the basic package, not the extended package Ford, and it's 100% is 230 miles. And we rarely charge it to 100. We usually charge it to 90 in order to make the batteries last longer.
So if you're leaving here and heading to Utah, you're probably stopping in Las Vegas.
Yeah. We're doing 10 charge ups, 8 to 10 from Apple Valley to Lehigh.
Wow.
Yeah, so we'll stop in Baker, we'll charge up. We'll stop in Vegas, we'll charge up. Mesquite. Then
That's roughly about 600 miles. If my calculations are right, that's about 600 miles.
Yeah.
Okay.
Yeah.
But you're pulling hills. You're doing a lot of elevation changes.
Yeah.
And
The hills really take it. And you get some back on the downhill, but on the uphill, it really hogs energy. Yeah.
Yeah. Well, maybe coming home, you don't have to do as many, but going up there, once you leave Las Vegas, you're probably on almost a constant incline. So, yeah. Cool.
All right, folks. Thanks for joining us. We'll talk to you later.
Take care, everyone. Thanks for joining us.